In this video, I will talk to you about multiple linear regression. So this is the hypothesis for more than one variable. The hypothesis is a linear combination of theta I xi with I from 1 to n, or you can write it in a vector form, which is theta transpose times x, and theta here is a vector of length of n plus 1 from 0 to n, and also x is a feature of vector also from x not to xn of length n plus 1. And now again we see the cost function j of theta, and we saw this before. Basically it measures the difference between h corresponding to the instance xi and the actual value or the actual target value yi. The difference is squared and summed from or for all the instances through the dataset. For multiple linear regression, the gradient descent update rule is more general. So we repeat and update theta j by that much again and again iteratively until the convergence, and the parameters are updated simultaneously for all theta. What is the partial derivative of the cost function respect to theta j? So basically taking the partial derivative of the cost function, you get this. This partial derivative is pretty much straightforward, and you have this term because so you can look at this. This is h parameterized by theta at xi, and it is a linear combination of theta j xji with j from 1 to n. So taking the derivative with respect to theta j, what you have left is just xji, and that is here. So finally, this is the gradient descent update rule, and it is a loop. You repeat again and again and update theta j, and theta j is getting closer and closer to the optimum point. The closer theta j close to theta opt, the smaller the change is. And with theta j we need to update simultaneously, and we talked about this previously. And basically we need temporary variables to store the computed values. So all the parameters theta j have to be stored temporarily somewhere, and then you update them simultaneously from the temporary variables. So in order to make sure the algorithm is working, we need to do some checking. Normally we plot the cost function against the number of iterations to make sure the cost decreases. And also we try a different step size alpha, and if the algorithm diverges, then reduce the step size. If the number of features is small, then we can apply the normal equation. So theta can be solved analytically, and this is theta, and the matrix X contains instances on its rows. Sometimes it may be better to fit that down using higher orders. So this is a case of polynomial regression. So looking at the data, the problem that we saw previously with S&P 500 and the security A. So it looks like that if we fit using second order, it may be better. So in this case, we map. So from this feature vector, we map to a higher order, and we have to be very careful that higher order or very high orders we call overfitting. And in general, we can use any functions such as exponential, log, inverse, and sine.